Hello everyone. My name is Dr.E.Purushotham, Professor of Physics, Department of Basic Sciences, School of Sciences and Humanities. Today, I am going to discuss about properties of nanomaterials. A warm welcome to today's lecture of properties of nanomaterials. So, you try to understand here clearly properties of nanomaterials. So you see here the physical, electronic, magnetic, and chemical properties of nanomaterials depending on sensitively on their particle size. You see here small particle displays behaviors that are different from those of the individual atoms or bulk material. So the different properties, first property, this is the physical properties of nanomaterials. The effect of reducing particle size. So particle size decreases, increase in surface area to volume ratio increases. So what I am saying here, if the nanoparticle particle size decreases, surface area to volume ratio increases. Increase in surface area to volume ratio, it gives the different properties. So it changes the surface pressure, results in the changing the interplanar spacing. Interplanar spacing. The interplanar spacing is represented by D. The particle size decreases. Particle size decreases. Surface area to volume ratio increases. Then this changes the surface pressure and the interplanar spacing. Therefore, the change in the interplanar spacing and the large surface area to volume ratio in particles. So you try to see here particle size reduces, its interplanar spacing also varies. You try to understand this d value. It is increasing d value. Here also increasing, here also increasing. You try to understand the interplanar spacing is changing clearly. So this is it represents that precise control of distances between gold nanoparticles. So particle size decreases, surface area to volume ratio increases, the interplanar spacing value also increases, that it changes, the surface pressure also changing. So convention of materials into nanoscale. You see here increases crystal performance or perfection, reduction of defects, which would result to the increase in mechanical. So what I am saying here, you see here conversion of materials into nanoscale. That means the nanoparticles particle size decreases. It increases crystal perfection or reduction of defects, which would result the increase in mechanical strength. So coming to cutting tools, which should be harder than the material which is to be cut or made of nanomaterials, such as tungsten carbide, tantalum carbide, and titanium carbide. So these cutting tools are much more erosion resistant and durable than their conventional large grained bulk material. So you can observe here in this figure and also in this figure, this is you see increase in mechanical properties by using nanomaterials can be used in motor vehicles, in these motor vehicles. So coming to electrical properties, surface scattering phenomena is highly increased due to reduction of particle size. Hence, there is increase of the total resistivity in nanomaterials. In nanomaterials, you can also observe in this group frequency versus this conductivity for 10 nanometers. This is 20 nanometers. This is 50 nanometers. In addition, a reduction in particle size below a critical dimension, that is, electron de Broglie wavelength, results in a modified electronic structure with a wide and discrete band gap. The reduction of particle size into this range results in an increased electrical resistivity. So, coming to optical properties, the properties like color and transparency are considered as optical properties. The optical properties are observed to change at nanoscale level. So, for example, bulk gold appears yellow in color, while in the nano size, gold appears red in color. So, you see here silver nanoparticles at around 100 nanometers. You try to understand this structure, crystal structure related SEM and this color. Gold spheres at 100 nanometer, you can observe this color. This is gold spheres at 50 nanometers, this is this color. Silver 120, the color is changing. Try to observe. Silver at 80, it is also changing. Silver at 40, so the particle size changes. The color of the color is also changing. So you try to see cadmium sulfide nanoparticles related in this figure. Bulk silicon appears gray in color, while nano-sized silicon appears in red in color. Zinc oxide at a bulk scale blocks ultraviolet light and scatters visible light and gives white appearance. So these are the optical properties. So magnetic properties, try to understand here. The large surface area to volume ratio results in a substantial proportion of atoms having different magnetic coupling with neighboring atoms, leading to different magnetic properties. For bulk materials, exhibits ferromagnetic nature usually from multiple magnetic dimensions. So small magnetic nanoparticles often consist of only one domain, and exhibit phenomena is known as superparameters. So here, just I given here diamagnetic, paramagnetic, ferromagnetic, antiferro, ferrimagnetic materials, but I am not giving the detailed explanation here. So coming to ferromagnetic materials, so take an x-axis external magnetic field, on y-axis super paramagnetic or magnetization M. The external magnetic field applying on the magnetic material. So the magnetization also increases rapidly up to point A. After point A, if you are reducing the magnetic field from the material, it can come back AO. After sometimes, if we are applying some magnetic field, it gets the saturation. So that magnetic field is called saturation magnetic field. That magnetization is called saturation magnetization. Saturation magnetization MS. If we are reducing the magnetic field from point A, it creates a new path, AO, new path, new path. So after that, if we are observing, so totally we can observe like this hysteresis loop, hysteresis loop of ferromagnetic material, hysteresis loop of ferromagnetic material. This is the hysteresis loop. So here saturation magnetization MS, it is showing here MS. So based on the surface area to volume ratio, nanoscale materials have increased total surface area, increased number of atoms accessible on the surface, increased catalytic activity of those large number surface atoms, different tunable surface catalytic property by the change in shape, size, and composition. Hence, nanoscale catalysts can increase the rate, selectivity, and efficiency of various chemical reactions. So you take here, take an x-axis particle diameter in nanometers, 0, 10, 20, up to 50. So on y-axis, take it reaction rate, mole per meter square per day. So effect of particle size on the reaction rate we can observe here in this graph only. So quantum confinement, size controlled electronic. Try to see here when dimensions shrink below the exciton Bohr radius, electrons and holes become spatially confined. So you can observe here clearly this is the photon energy, how it is moving like this. So conduction band, valency band, this is molecule related one, this is nanocrystal, this is bulk crystal. This leads to quantization of energy levels, unlike continuous bands in bulk material you observed in valency band and conduction band. So as the size decreases, band gap energy increases. You see here, from here to here, it is increasing, leading to tunable optical and electronic properties. In quantum dots, different sizes emit different colors. An application of this principle we can observe. Nanoscale semiconductors thus enable color specific bioimaging and photo detecting. So electronic density of states becomes discrete drastically, affecting conductivity and absorption. These effects revolutionize applications in optoelectronics, photovoltaic, and photonics. So physical properties. You try to see here property, change at nanoscale, advantage gained, and application. At this place, we are trying to understand clearly the physical properties. So you see here physical property, mechanical strength. So you see here increase due to the grain boundary, strengthening, that is called Hall fetch effect. So advantage is higher durability, where resistance is the advantages of this physical property. So these are used in aerospace materials, nano coatings, micro electrochemical systems MEMS. This physical property helps to aerospace materials, nano coatings, micro mechanical systems. So physical property, that is hardness, typically increases in nanocrystalline materials. So improved, you see here advantage, improved scratch and wear resistance due to the hardness. So hard coatings for tools, armor platings, we can paint. Elastic modules. So you see here may increase this physical property due to the elastic modules. Carbon nanotubes have extremely high modulus. So structural stability at lower weight is the advantage of the physical property of nanomaterials. Lightweight composites, these are available in lightweight composites for aerospace and automotives. Ductility. So what is the change at nanoscale? Often decreases due to the dislocation confinement. What is the advantage? Enables super strong hard materials. So these are used in nanoceramics, protective wear resistance films. Coming to melting point. The melting point decreases. Particle size decreases, melting point also decreases. So this melting point depression in nanoparticles. What is the advantage? So easier to process or sinter at lower temperature. This is the advantage. What is this application? Low temperature sintering, nano soldering in electronics. Simply comparing the advantage and application. So coming to this density, how it is changing, we try to understand. Slightly altered due to the porosity, surface, atoms, and defects. So we will get the tuned mass properties. This is the advantage. So this nanoporous materials for catalysis and filtration. These physical properties, due to these physical properties, we can use the nanoporous materials for catalysis and filtration. Surface energy property increase significantly due to high surface atom ratio. The particle size decreases, increase the significantly due to high surface atom ratio. So the advantage is enhanced chemical reactivity. The application is catalyst, energy storage, that is lithium ion batteries, and these are used in supercapacitors also. Thermal conductivity, another physical property. So change at nanoscale increase significantly due to the surface area, increase in surface area to volume ratio or high surface atom ratio. The advantage is gained here, enhanced chemical reactivity. The application is, that is catalysis, energy storage. These are used in lithium surface energy related, but here thermal conductivity can increase carbon nanotubes or decrease nanocrystalline metals. So the advantage gained, that is controlled heat flow pathway. Application, you try to understand here, nanothermal insulators, thermal interface materials. Coming to heat capacity, oh, this is the physical property. So the change at nanoscale, deviation at low temperature due to the phonon confinement, better energy storage and dissipation control is the advantage of this heat capacity. The heat capacity application is cryogenics, thermoelectric materials. These are used in this thermoelectric materials. Diffusivity. So increase significantly. Faster atomic mobility and reaction is the advantage of this physical property. So application is sintering, catalysis, nanoceramics, manufacturing. Coming to chemical properties. Yes, chemical properties. Chemical property, you see here, chemical reactivity. So the change at nanoscale, you see, significantly increases due to high surface atom density and surface energy. What is the advantage? You see here, advantage is it is faster, more efficient reactions. It gives the perfect reactions. So application, the chemical reactivity application is catalysis, energy, environmental. What are the examples? Nanocatalyst in fuel cells, carbon monoxide oxidation, water splitting. So redox behavior also we can understand here. Altered redox potential due to the quantum confinement and the surface state shift. That is the change at nanoscale. Advantages are that is tunable oxidation, reduction reactions. Application is energy storage sensing. So these are used in energy storage sensing. What are the examples you see here? Electrode materials in lithium ion batteries and supercapacitors and supercapacitors. So next one you see here solubility and dispersibility. What is the nanoscale change you see often enhanced in polar or non-polar solvents due to the surface modifications. Advantage. It is easier processing, improved interaction with biological systems. So it is used in biomedical drug delivery systems. What are the examples? Drug carriers, nano dispersions in pharmaceuticals. Surface functionalization. So the nanoscale changing is increased capacity for surface functional group or coatings. What is advantage? Tailored surface chemistry for selective interaction. So these are used in biosensing targeted delivery systems. Examples: antibody functionalized gold nanoparticles for cancer detection and therapy. Corrosion resistance. So the nanoscale changing may increase or decrease based on surface passivation and morphology. What is the advantage? You can see here controlled corrosion for desired environments. That is the advantage. So biomedical implants and coatings are the applications of chemical properties. So titanium dioxide nano coatings for corrosion resistance, orthopedic implants, these are the examples. So photocatalytic activity greatly enhanced to band gap tuning and high surface area is the nanoscale change. So the advantage is efficient light driven reaction and application environmental renewable energy related applications we can observe here. What are the examples? Titanium dioxide, zinc oxide nanoparticles in dye degradation and hydrogen generation we can use. Chemical stability. Some nanomaterials become less stable due to high surface energy and oxidation tendency. These are the nanoscale changes. What is the advantage of this chemical stability? We can be stabilized through functionalization. This is the advantage. These are used in packaging, coatings, and electronics. What are the examples? Silver nanoparticles in antibacterial coatings with surface capping agents. These are the applications and examples. So, coming to next one, chemical properties, a summary of key changes and benefits. You see, change in mechanism, high surface area to volume ratio. Why it happens, we try to understand here. More relative atoms exposed at the surface. Due to this high surface to volume ratio, we can get. Then it increased the chemical activity and surface reactions. Quantum size effect. So, due to the quantum size effects, alters energy levels and electronic structures. So, the bulk material is divided into small pieces. The energy levels are changing. The changing energy levels gives the quantum confinement effects. It changes the quantum size effects. So, due to this, altered energy levels and electronic structures, it is tunable, redax, and optical properties. You see here surface defects and curvature. It enhances active sites and reactivity. It changes the mechanism. Then effective heterogeneous catalysis we can observe. Coming to here, tunable surface chemistry. Surface can be engineered with ligands or functional groups. Due to this, we can observe the selective binding compatibility with the biological systems. So, coming to chemical properties, application areas, and examples. So, you see field, energy field, nanomaterials based chemical advantage is high surface redox activity, tunable conductivity is the nanomaterial based chemical advantage. So the examples are nano titanium dioxide in solar cells, NiFe2O4 for oxygen evaluation reaction are the examples of energy field. So environmental remediation. So it enhanced photocatalysis, adsorption, or the nanomaterial based chemical advantages. For these examples are ZNO, titanium dioxide for dye degradation, nanoscale, zero valent iron for water cleanup. So biomedical field, biomedicine field, functionalization for targeting controlled solubility or the nanomaterial based chemical advantages. The examples are you can see here drug loaded liposomes, PE gylated nanoparticles for cancer therapy. So, in sensing field, try to understand high sensitivity due to the surface chemistry and redox shift is the nanomaterial based chemical advantages. So, gold or graphene oxide nanosensors for glucose, pH, or metal ions are the examples. Coating paints, controlled reactivity, and anti-corrosion are the nanomaterial based chemical advantages. The examples are nano silver, nano zinc oxide in antimicrobial coatings, catalysis field. So active surface and selective functional groups are the nanomaterial based chemical advantages. Platinum, PD, RM, gold, nanoparticles for industrial chemical synthesis are the examples of chemical properties. Chemical properties. So coming to optical properties. Optical properties. This is optical property change at nanoscale, advantage gained and application area examples of applications. So this is absorption spectrum property. You see here broadens and shifts. These are the change at nanoscale. Tunable absorption for specific wavelengths are advantages gained here. So these are used in solar energy photo detectors. What are the examples you can see? Quantum dots in multi-junction solar cells, PBS, QDs, quantum dots in IR detectors. You try to understand here emission spectrum, that is photoluminescence. What is the change at nanoscale? Simply understand becomes size dependent and sharper. So we can observe different color tuning for optical displays and biological label. So these are used in bio magging, light emitting diodes, display technology also. So cadmium, selenium, CDSE, ZNS, quantum dots for RGB display, pixel or fluorescent tagging. So refractive index property also we can observe here. These are used in materials photonic crystals. So nanostructure photonic materials with engineered light paths. Surface plasma. The application is sensing imaging photothermal therapy. Gold nanoparticles in biosensors, plasmonic heating for cancer therapy. These are used in. So scattering property, transparency property, nonlinear optical responsible, photothermal convention, number of properties we can observe here. These are used in sensor optical coatings, electronic smart windows. The optical properties of nanomaterials are used in telecommunication laser technology, biomedical catalysis, time gated, biorelated, they are used. So coming to this optical properties, summary related, you try to see here. So mechanism, why it happens, resulting change, try to understand very simple. Quantum confinement effect. Due to the discrete energy levels form as electrons are confined. So result change, tunable emission and absorption we can observe due to the quantum confinement. Surface plasma surface plasmon resonance. So why it is happening? Collective oscillation of surface electrons in metallic nanoparticles. It gives the result the intense light absorption or scattering at specific wavelength. High surface area. So more active optical sites, due to the more active optical size, we get the high surface area. This high surface area give enhanced photoluminescence and light matter interactions. Reduced dimensionality alters light propagation and scattering behavior. It reduces dimensionality. Then, due to this result, we try to understand control over reflectivity, transmission, and refractive index. Yes, optical properties, continuation, you can see. Biomedicine. So, tunable related, we try to understand here. Fluorescence and SPR. So, examples, quantum dots for tumor imaging. So, gold nanoparticles for biosensing and therapy. That energy field. Enhanced light absorption and scattering, nanomaterial based advantages. So, nanostructured titanium oxide in dye sensitization solar cells are the examples. Display technology. So, nanomaterial based optical advantage is bright, tunable emission with a long lifetime. It has a long lifetime. It is the advantage. So, example, quantum dots in QLED TVs. This is the example. So, sensing field, SPR based signal amplification is the advantage. So, example, LSPR biosensor for DNA or protein detection. Photonics or optoelectronics field. So, the advantage is light manipulation and nonlinear response. Photonic crystals, optical switches are the examples. Catalysis process, photothermal effect, and light triggered reaction is the nanomaterial based optical advantage. The examples are plasmonic nanoparticle catalysis for light driven chemical reactions. Coming to electrical properties. Electrical properties. Yes, you see, this is the electrical property, change at nanoscale, advantage gained, application area, examples. So, electrical property, that is the conductivity. So, nanoscale changing, we can observe clearly, can either increase or decrease due to surface scattering and grain boundary effects. Due to this, we can observe the conductivity. What is that conductivity advantage? Tailored conductivity for these devices. So, this property is used in nanoelectronics and sensors. Example, silver nanowires in flexible, transparent conductors. This is the conductivity property. Electron mobility. So, due to the reduced to enhanced surface and grain boundary scattering, this is the nanoscale change. What is the advantage? High speed switching in short channels we can observe. So these are used in transistors, logic gates. What are the examples? Carbon nanotubes, FETs, graphene based devices. So quantum conductance. So how it is the changing up to nanoscale? You see, conductance became quantized in one-dimensional systems. So the advantage is enables ultra low energy electronics. So here quantum computing, nanotransistors, these are used in quantum computing and nanotransistors. Example, single atom wires, quantum point contacts are the examples of this electrical properties in that electrical property that is quantum conductance. Tunable current property, these are used in flash memory, tunable FETs. Examples, STM tips, flash, NAND memory, tunable junctions are the examples. Dielectric contact are used in energy storage, nanocapacitors. The example, barium titanate nanostructures, HFO2 films. Work function also, you try to understand application catalysis, vacuum electronics. Example, nanostructured electrodes in fuel cells related. Band gap also, these are used due to this band gap LEDs, photo detectors, solar cells. So, ZNO, CDSE, PBS, quantum dots, examples. Charge storage capacity. You see here, these are used in supercapacitors, lithium ion batteries. Examples are MnO2 nanosheets, RGO based hybrid electrodes. So, coming to next properties, that is mechanism, simple explanation, and impact. So, you see quantum confinement effect. So, due to the changing of energy levels, it becomes discrete due to the spatial confinement of electrons. Impact is alters band structure, band charges, transport. Surface to volume ratio. Dominance of surface atoms alters carrier scattering and energy barriers. So it gives the impact, effect, conductivity, and charge trapping. Electron tunable. Electrons can pass through the barriers thinner than approximately 2 nanometers. So it affects on enables non-classical current flow. So coming to this Coulomb blockade, blockade. Energy required to add an extra electron becomes significant. It affects or it is useful for quantized current and digital logic at nanoscale. Yes, coming to next one, electrical property, nano electronics. So low power consumption, faster switching are the advantages of this nano electronics. So CNT, carbon nanotubes, FETs, FinFETs, and SETs are the examples of these electrical properties related. So energy storage application area, high capacitance and fast charging is the advantage. The examples are supercapacitors with porous nanocarbons and hybrid electrodes. Sensors related application area. So the advantage is high sensitivity due to the enhanced charge interaction. Graphene and zinc oxide, nanowires, gas sensors, FET based biosensors are the examples of sensors in electrical properties of nanomaterials. Photovoltaics. So these advantages are tunable band gap and improved charge separation. Examples are quantum dot solar cells, perovskite nano hybrid solar cells. So flexibility also we can observe here. Quantum computing, the advantage control over single electron transport. Examples are qubits in quantum dots, Josephson junction arrays. So these are the examples. So try to understand here summary in these physical properties. The interatomic spacing decreases with reducing size. By reducing particle size, increase of surface area to volume ratio is noted. This affects the melting point of the material. The melting point decreases with size, and at very small sizes, the melting point decreases is very fast. So try to understand here the particle size decreases, interatomic space decreases, then increase in surface area to volume ratio. It affects the melting point of the material. Particle size decreases, melting point also decreases. Try to understand clearly. The interatomic spacing D with reducing size, that is particle size decreasing. By reducing particle size, increase of surface area to volume ratio is noted. This affects the melting point of the material. The melting point decreases with size, and at very small size, the melting point decreases. Decrease is very fast. Coming to chemical properties. You see here, simply try to understand the reduction of particle size have a strong effect on catalytic property. Particle size decreases, ionization potential increases. This is the simple chemical property. The reduction of particle size have a strong effect on catalytic properties. The ionization potential at small sizes are higher than that for the bulk material. Small particles may be very useful in hydrogen storage devices in metals. So coming to another one, electrical property. In nanoceramics and magnetic nanocomposites, particle size decreases, electrical conductivity increases. Various in metals, electrical conductivity decreases. That is electrical property in simple way. In nanoceramics and magnetic nanocomposites, the electrical conductivity increases with reduction in particle size, whereas in metals, electrical conductivity decreases. Coming to optical properties, optical properties. The optical properties are depending on particle size PS. The particles can be made to emit or absorb specific wavelengths, that is called colors of light, just by controlling their particle size. What I am saying, the optical properties of the particle can be finely tuned depending on its size. Thus, particles can be made to emit or absorb specific wavelength, that is colors of light, just by controlling their size. So, coming to magnetic properties, magnetic properties. The strength of the magnet is measured in terms of coercivity and saturation magnetization values. These values increase with decrease in particle size and increase in surface area to volume ratio. So you try to understand here, take an x-axis magnetic field, on y-axis magnetization. So we get the hysteresis loop of ferromagnetic material. From this point to this point, it gives the coercivity Hc, or this point to this point plus Hc, coercivity Hc. The strength of the magnet is measured in terms of coercivity Hc and saturation magnetization. This is the saturation magnetization Hs. These values increase with the decrease in particle size and increase in surface area to volume ratio. What I am saying here clearly, magnetic properties, try to understand the strength of the magnet is measured in terms of coercivity and saturation magnetization values. These values increase with a decrease in the grain size and an increase in the surface area per unit volume of the grains. Small particles are small particles are more magnetic than the bulk material. Nanoparticles of non-magnetic solids are found to be magnetic. What I am saying here, the strength of the magnet is measured in terms of coercivity, Hc, and saturation magnetization, Ms values. These values increase with decrease in particle size and increase in surface area to volume ratio. So, mechanical properties. Because of nano size of particles, the mechanical properties such as hardness, elastic modules, fracture toughness, etc., are modified. So, these are the properties of nanomaterials. Thank you. Thank you so much for selecting and observing this video. Thank you. Thank you so much.